So I have 5:10, so I'm going to get started. People may still straggle in, so thanks everyone for coming. I know it's like the last talk of the day. Hopefully we'll get out a little early so we can get food early. So a couple of things just before I get started. So I originally gave this as a 10-minute talk at a conference called Bang Bang Con. Bang Bang Con is a kind of like 2 days of lightning talks about joy, excitement, and surprise in computing. One of the rules, if you submit a talk there, is that you have to have at least one exclamation point in the title. So I kind of kept that. If you notice, my abstract had a lot of exclamation points. A lot of the slides have exclamation points. Sometimes the people didn't probably have the exclamation points in what I'm quoting, but they really meant it. So with that, I also should say that there's not really very much Perl in this talk. There's a little bit of Perl at the very end, so if you're here for a Perl talk, you might want to go to one of the other ones. Having said that, so my name is Walt Mankowski. I am, at this point, a recovering ivory tower computer scientist. I used to work with biological images and tracking cells, which is very cool. Now I work for a company called PsyApps that does precision medicine, which involves helping oncologists find the right, navigate the world of biomarkers and clinical trials to helping cure cancer, basically. And I should say, contractually, I have to say we are hiring because everyone's hiring. We don't really do any Perl there, unfortunately. But if you're interested, still come see me afterwards. But a long time ago, back in the 90s, I worked for a large cable home shopping station called QVC. For most of the time I was there, I was a COBOL programmer. I worked on some other things too, but most of the code I worked on there was COBOL. So I know what most people think of when you think of COBOL. You think of this, right? And to be honest, this is what I thought of too. Someone made a note. I found this. I don't even know where this came from, but I really like that slide too. But as much as we want to think of COBOL as being a dead language, it keeps coming back and back. If you were at my talk I gave at YAPC a few years ago, I had this slide then. It still kind of blows me away. Even though all the press goes to the internet startups and things, I mean, really, COBOL is still there behind the scenes, handling all the credit card transactions, making sure your iPad makes it from Shenzhen to the West to Apple so they can ship it. All those shipping crates going across the oceans, it's all being managed by COBOL behind the scenes. And you can still make a lot of money at COBOL, right? If you remember when I gave this talk, I talked about there are some things that COBOL is still pretty good at. And if you don't believe me, you can believe him. This is Brian Carnahan. Of course, one of the inventors of C. He's now he's a professor at Princeton now, a computer science professor at Princeton. So he left Bell Labs quite a while ago. And he said COBOL was really good at handling formatted data, which it is. It is really for certain types of formatted data. I think it is probably one of the better languages out there. But that was, I already talked about what I thought COBOL was good at, so this year was time to talk about things that COBOL was bad at. And there's low-hanging fruit, right? I could talk about its propensity to generate spaghetti code, but I should say also that when I showed this slide at the Philadelphia Linux Users Group, some people were offended by this picture, so if I'm violating the code of conduct, so this is totally aside, but if you work with biologists at a university, you get occasionally dragged to talks that you don't quite understand, but sometimes they have really cool pictures, like these. These are protein folding diagrams, and so this is kind of proteins, which are like the building blocks of our lives, look like this. And all I'm saying is, I think that we are kind of made in the image of his noodly appendages. So it's just something to think about. Anyway, so I didn't want to talk about, this is enough about spaghetti code. I want to talk about something that I think is more interesting. So going to talk about a bug I ran into while I was working at QVC. And obviously, I would say, like, I don't have the code. I'm regenerating it from the thing that happened. So has anyone ever used, I should ask, anyone ever used COBOL here before? A few people. I did it for a class. Ran out of like, okay, that's fair. It is designed to be pretty simple to understand, so I can sort of step you through what's going on here. So these are some variable declarations. One weird thing about COBOL is sometimes when you declare a variable, you could say how you want it to look like when it gets printed out. So instead of having like a printf statement in C or in Perl, you can say in the description of the variable what it should look like. So for instance, a pick x2 is something that's 2 characters long and can be alphanumeric. That's what the x stands for. And value means that's what its default value is, so it gets initialized to that. A pick 9 is something that can only be numbers. A pick 9 V999 for the shipping charge, that's a way of doing a number with a decimal point, so it'll always be 2 decimal points before, 2 numbers before the decimal point, 2 numbers after the decimal point. So you won't have any kind of round off error, which is nice. I'm sorry?
Amazon Prime picked up.
Well, this was in like 1997, so things were cheaper then. So what I'm trying to do here is if someone's paying by FX was Federal Express, they're going to get, so if they're paying by Federal Express, they're going to get this expedited ship date. And I have the dates from like when Bang Bang Con was last year. So if you pay by anything but Federal Express, you get something that was like 2 weeks out. Otherwise, you get next day delivery. Okay? And then, if you're an employee, you get free shipping. If you're paying with a QVC credit card, you get free shipping. Everyone else gets the default values that are up there. And then at the bottom, we have display as like a print statement. So it prints the expected shipping date as being 5/22, and that's because they're paying with they're just shipping it US, which was US mail, so they should get the date that's 2 weeks out, so that's fine. Now, we expect the shipping charge to be 0 because they're an employee. They should get that. However, the shipping charge is actually $4.99. So what's going on there? If you know, don't say. Have you used COBOL? Do you know what it is already? You can guess? Well, okay. So I will give you a hint, and then you can see whether you're close or not. So when I did this, I really didn't have any idea. But now, if you load it in, I tried this both in Vim and in Emacs, and both times it flagged that period as being problematic. Is that what you were thinking of?
No.
Okay, then you were wrong. So the period is what's wrong there, but it wasn't clear to me why the period would be there. So you can't see it. Like, what's going on there? So the whole rest of the talk is explaining why that period is an error in this program, or we'll get to that. So before we can really understand that, we have to have a little bit of a history lesson. So this woman is Jean Sammet. She just passed away last year. She's got this great quote. She always thought of a computer as an obscene piece of hardware that she wanted nothing to do with. So so when she passed away, she actually had obituaries both in the New York Times and because she had been president of the ACM, she had an obituary, the communications of the ACM as well. So she really was one of the pioneers of COBOL, maybe possibly even more so than Grace Hopper, because Grace Hopper, I think, was maybe more of a manager of it and sort of leading things, but she was kind of down in the trenches, actually writing the code for the initial versions of COBOL. Later on, she went on to a pretty distinguished career in computer science. She worked on programming languages and computer algebra, and as I said, she was president of the ACM for a number of years. So pretty impressive person. The quote I had from Brian Carnahan was from the obituary in the New York Times for her. Of course, this is Grace Hopper, who's probably most closely associated with COBOL. She's got this great quote that I love. I'll read it if you can't read it. Humans are allergic to change. They love to say, we've always done it this way. I try to fight that. That's why I have a clock on my wall that runs counterclockwise. And that's a great quote, but it kind of sounds ironic when you think about COBOL in 2018, when we think like those dinosaurs, right? Like it's such a backward language. But really, for the time it was created, it was a super radical language. So it was created way back in 1959, so it's almost 60 years old. So its design goals were several. It wanted to have an English language syntax as opposed to languages like Fortran that look much more like mathematics. We saw the code before that I showed you. It looks more like English language, which was a pretty radical idea at the time. And also it was designed not for things like COBOL was doing, like scientific experiments, missile trajectories, things like that. It was designed for business computing, for expense reports, personnel records, things like that. So if you ever have used a computer for a spreadsheet or to figure out what your taxes should be at the end of the year, or to make a presentation like Guy and lots of people are doing here, you kind of have Grace Hopper and the people behind that to thank. So let's talk a little bit about the English language syntax. So, anyone know what this is? This is the BNF format for a statement in the C programming language. So, what I've highlighted here is some things for how an if statement works. So, a statement can be a number of things. So it can be a labeled statement, an expression, compound statement, and a selection statement. So what's a selection statement? That's an if, and a statement, an if statement, else statement, or you can have a switch statement. Each of those statements is recursively defined to be the statement up at the top. So you could have, ifs and nested other ifs and ifs and else nested, just like we have here. And this seems perfectly normal for us today, right? Like you don't even think anything of that. That's because C and Perl and pretty much all the languages that came after C are, almost everything is defined recursively, just like that crazy BNF format that I showed you before. COBOL's not like that. The COBOL's language is hierarchical. So at the top level, there's program, and divisions and sections and things like that. But it is not recursive like we saw before. So what does that really mean? So for the example of if statements, there's two different ways to do if statements in COBOL, or to do block statements. An if statement is an example of that. One is you can have scope terminators. So every time you have an if, you have to end it with an end if. If you have a perform, you close it with an end perform. And that's what I've showed here. And that doesn't look so much different than it would be in C or Fortran, C or Perl. Actually, MATLAB still uses end ifs like that today. The other way you can do it is to have implicit termination. So the entire thing ends with a period. That's because this is all a sentence. What does a sentence end with? A period. So that's all one statement, and it ends with a period. So how do you make sure that that move A to C goes with the outer if instead of the inner if? You have to say next sentence. So if it doesn't meet this condition, it goes to here and drops to the next statement after the period. Otherwise, it executes this, and then this goes down with that. So do you all follow that? This is kind of important to what I'm getting at with the period thing in mind. So, okay, so two ways to make if statements. One issue is that this syntax is from COBOL 85. So remember, COBOL was created in 1959. So what is that? 26 years of COBOL code, where the only way you could make if statements was, closing that was with periods like that.
Why did they change it? It's a completely different language.
Exactly. And we'll get to that too. We'll get to that too at the end.
They should have thought COBOL Then it still wouldn't be out.
So, and of course, even with this, it did take quite a while to sort of roll this all out. We had two different systems that I worked on at QVC. One used the top syntax for if statements. The other one used the bottom statement for if statements. The bottom syntax for if statements. If you look at this code I have here, it's using it's not using end ifs. All the ifs are terminated with periods. Okay, so that's one reason. So the other thing that's going on here is that the world was a pretty different place back in 1959. This is what a 5 megabyte hard drive looked like around then. And this is a punch card, right? The punch card was in the name of the talk, so we knew we were getting to them somewhere, right? So how old of a technology do you think punch cards are? Anyone? Steven. What? Jacquard Looms. From what year? No. 1880s.
Jacquard Looms are much older.
They're much older than that. Right, around the turn of the 19th century. So this is Joseph Marie Jacquard. So he developed a loom. I don't know. I saw 1801 somewhere, 1804. It was like around that time, the very early 1800s. I'm sorry.
1804.
1804. Thank you.
I can edit the page if you need me to.
So this picture was woven on silk using 24,000 punch cards. It's pretty cool. So I found this great video of how Jacquard looms work. And I'll kind of talk over this a little bit. It's very clever. So there's just subtitles. There's not any sound with it. So the idea with weaving is that you've got a whole bunch of threads held very tightly that are vertical, and you weave a looser thread horizontally, either above or below the tight threads. And then depending on whether the vertical threads appear or not, that's how you get patterns. Right, so that thing he's pulling is what moves the loose thread back and forth, the horizontal thread. But the pattern's encoded in punch cards, which you'll see pretty soon. Right, this is all like mechanical. There's no engines or anything driving this. I'm sorry? Yes, it's a stand-up desk. It's very much ahead of his time back then. See, he says 1801, so who knows? Who knows whether it's 1801 or 1804?
He probably started with flash drive.
Right, so he's basically doing, you can't see, but that's like graph paper. So he's kind of making a bitmap on graph paper of what the design should look like. And then he's got this machine that encodes it into punch cards. And then it's very, well, remember what that looks like. We'll talk about that in a second. So they all go through, and whether there's a hole or not, there's some hooks that either fall through or don't fall through. And then if they fall through, they pull the thread down. If they don't fall through, they stay where they are. And then, no, it's just the opposite. They get pushed out of the way if it's not. Yeah, and that's how it works. And when they do that, they pulls the threads up, and that's how you get the patterns encoded. So other people tried to do this. They had the idea of encoding the patterns in paper like this. I think his innovation was that other people had tried to use things that were more like player piano reels, and he uses these, you can tell there's like very kind of thick cardstock and kind of small things that are tied together just with twine, and that makes it a lot more flexible. If you lose one of them, you just have to replace that one little piece instead of the entire thing. They're a lot more durable, they can fold more easily, they can fold on where the twine is. So, pretty cool. The next person in our world here is Charles Babbage. He's sometimes called the father of the computer. He designed these two things, an analytical engine and a difference engine. The analytical engine, the difference engine, which is something I think they did actually build in, I'm sorry? Right. The analytical engine was something that, like, it was way ahead of its time. Like, it probably could not have been built the way it was. But it was something that was supposed to be basically a programmable computer. This is a scale model from the London Museum, and the idea was that you would encode the programs in little punch cards, which look a lot like Jacquard's punch cards, right? Because he was doing this about 50 years after Jacquard has invented his machine, so it's a pretty well-known technology. This is Ada Lovelace, who famously worked with Babbage on his machines. He said, the analytical engine weaves algebraic patterns just like Jacquard Looms weaves flowers and leaves, which is kind of a beautiful thought, I think. This is Herman Hollerith, who is famous for really using, so the punch cards that Jacquard was using were kind of a program that was like just saying how it was driving that machine. It was sort of like control software in some very early sense. He had the idea that you could use punch cards to store data as well. He was inspired. He claims that he did not know about Jacquard Looms. I don't know if I believe that story or not. There's a story that he was on a train where they were worried about people stealing tickets or like using tickets for other things, so they were punching in not just whether you had used the ticket, but how tall you were. So like, whether you're male or female, whether you were, I don't know, what eye color you were. So things like that, so you couldn't use the ticket, like only the person who bought it could use the ticket. So the idea that you could automate that and store information on punch cards instead of just using it as control software. He used this idea for the 1890 census, and then he went on to develop the first working tabulating machines and card feeders, a key punch machine. He was one of the founders of IBM. And he had a pretty awesome mustache, I think. So this is what one of his punch cards from the census looks like. They look a little different than more modern punch cards. One thing is that it's smaller. There's not as much information being encoded there. Also, the holes are circular, whereas they became rectangular later on. And basically, these are all zeros and ones. So everything is a zero except where the hole is. That's a one. Yeah, like player pianos are sort of the same idea as that, except that's on more of a paper tape, but it's the same idea. This is a key punch machine from Bletchley Park that had been used, or a punch card reader from World War II and trying to break the German codes. Of course, these are AllStar Ballots, which were used up until 2014 to vote for baseball AllStar Ballots. Famously, they were still being used for to tabulate U.S. elections through the 2000 election. I love that picture. Sorry? Hanging chads, yes. So this is, like, at the time of the 2001, like the 2000 election, I don't know why I say 2001, I guess that's when they were counting them all up. I mean, it was like 200-year-old technology at that point, right? So let's talk a little bit how they worked. So this is what like a sort of standard punch card looks like. There are 80 columns across. There's actually 12 up, even though it goes 0 through 9 in rows. There's actually 2 more rows above, and we'll see some examples of that. They were designed sort of cleverly to be the size of US currency up until about 1928 or 29. I think Hollerith's idea was that when they shrunk the currency size down, there would be a lot of old bank trays that wouldn't be used anymore, and he could use those to store his punch cards instead. So let's talk a little bit about how like the data was encoded on there. So this is a punch card with, it actually, although it's impossible to read, it actually has all those letters I added up on the top are written on the top of the card. It's very dark, and I'm a little unsure of some of the punctuation marks here. So there is some letters up there. The letters are solely for human reading, because the machine that's reading it is only looking at the holes. So it goes 0 through 9, and then A through Z, and then a bunch of punctuation characters. So notice that this is not being encoded the most dense way possible. So 0 through 9, 0 is no holes, 1 through 9 are a single punch. A through Z are 2 punches, 1 up at the top, and then it kind of goes in order like that. And then we're using basically nothing up at the top, 1 or the first row or the second row. And then the punctuation characters get a little crazier after that. This kind of always confused me because when I saw some punch cards when I was like kind of breaking into the industry, I assumed that they were encoded in EBCDIC or something, but they're really not. They're like their own special way of doing it. So they pretty clearly were doing this so you would only, for a letter, would only ever have like 1 or 2, maybe 3 punches in any row. Do you know why they did that? Anyone have a guess?
So don't rip up.
Right, this is what they look like if you punch every hole in it. And right, these were just jam up in the machine. So they were really designed, like, they actually have like, it's 2 to the 12th, right? Because there's 12 bits in everything. So you have a pretty wide space, but they're not using everything because they want to avoid this problem. So it's important to understand that like this stack of cards, so this is what like an entire program would look like. And this stack of cards might be like literally your only copy of the program. It's not stored on a hard drive anywhere. It's not on a floppy disk. It's not on a flash drive. This is it, right? And if you were to drop this or lose it, it's gonna ruin your day. So you can kind of see some hints for what this person has done. They've written some text along the sides of them so that they can see what it is. They drew a diagonal line, so if they dropped it, they could kind of use it to put it all back together. Do they have sequence numbers on here? They don't, but we'll talk about like sequence numbers. Like you could reserve some characters at the beginning for sequence numbers so that if you ended up dropping them, you could use a mechanical sorter to put them back into order. All right, so this, I love this picture too. This is from NASA in 1957. This gentleman here is looking at an IBM 704 computer, and the young lady is working on an IBM 711 punch card reader. So there were some separate machines to punch the cards in, which look kind of like very noisy typewriters. And this is a punch card reader. So it was the most popular card reader at the time. But it only read, remember there were 80 characters across, but it only read 72 of the 80 columns. And the reason for that is that it read the data into 2 36-bit words. So the other ones were just dropped. And they could apparently move them so that any of the 72 out of the 80 could be used. But this is, again, just what I've learned from Wikipedia. They almost always just use the first 72. Okay, so this is a Fortran, a part specifically done for Fortran. And so you can kind of see that they drew lines here. So they're using the first, I think, 1, 2, 3, 4, 5 columns for a statement number. This is a continuation character, so if your line is longer than 80 columns, maybe 72, it can wrap around and continue on to the next line. The statement, it actually is written up there. It says Z sub 1 equals Y plus W sub 1. I don't know what that means. And then they drew another line here at the end, and they reserved the last 8 characters for an identification region. They call this Proj 089. So you could sort by the statement number, although they don't seem to be using that. You could also use this for like a subroutine. So you could sort by that and then sort by the sequence number, maybe the opposite. I have to figure out which one you want to do. So that was what Fortran used. COBOL had a more complicated system where the first 6 characters were the sequence number. The 7th one was an indication for comments or for continuation characters. A through 11, or 8 through 11, area A was just the division section or procedure headers could go there. Everything else started at area 12, at line 12. It also was ignoring columns 73 through 80. That was the program name area. So it only leaves you, I wrote it down here, 61 characters to actually put any code on any one line. They have, at some point, merged area A and area B together, but it's still only like 65 characters, so it's not very much. So also, like in the early days, they didn't even have terminals to type things in. Terminals didn't really become practical to use to enter code really until like the late 60s, and I think punch cards were still being used probably until like the 80s. They were just being phased out in the mid to late 80s when I broke into the industry. So you would write your code, your program on paper in specially formatted things called, I don't know what these things were called actually. But you write your code here, and then you would give this to someone who would key punch it in, and then you would run a job, and then maybe when it would get run, you would get the output, and so you could not like continuously test and fix things all the time. It was quite an involved process. But you can see here that even on this, they've sort of drawn lines for where the sequence number is, and the continuation area, and the identification area. Here's another coding sheet I found where they didn't even bother with anything after column 72 here. So, what does that mean for our program that we saw before? Okay, so there's the program. So I should say I cheated a little bit here because I wasn't showing the end. So really, the entire program, you can see I had really indented everything, right? So
That was going to be a procedure.
right, so let's put a ruler here, and that period is in column 73, which really meant that the period was totally ignored, which meant that this if statement was really part of the outer one. It said, you see what's going on there. So it's part of that else statement and then part of the if. So the way I fixed this was I just moved it over one space to the left, and now my period is at column 73. I'm told that
Use a shorter variable.
or use a shorter variable name, or you rearrange the code. I sort of set it up to work that way. There's lots of ways to fix it. I'm told that mainframe programmers that had to deal with it all the time sometimes would put a string down column 73, between 72 and 73, so they could see when they're hitting that. Like you would just be aware that this would happen. It's also easier to see because we would they would use column 73 through 80 for comments or revision things, because they did, also remember they didn't have anything like, they did not have Git back then. We would put revision numbers just at the ends of the lines, because those are essentially comments, so you have to use them for something, yeah.
Do you think, have you tried to write like Git in COBOL?
To write Git in COBOL, it would be difficult to write Git in COBOL. I have not tried to write Git in COBOL. So this was really odd for me because if I were to have written this in the system, so I really only encountered this because I had been working on the customer service system, which didn't code it this way. The order entry system worked this way, and we had been sort of, we only worked on our own systems, and after a while I'd been there and said, oh, well, everyone should sort of work on everything together. The way I would have written this in the system I normally worked on was like this. I would have put the end ifs after every one of the if statements. It also lets you, although you can't see me because I got rid of the outer things, it lets you start at column 1 instead of column whatever I started at, 7 or 8 or 11. So you just get more space anyway, so you wouldn't have run into it because of that.
So did COBOL 85 get rid of the 72 character?
I forget which version of COBOL, but yeah, at some point they allowed you to just write free-form COBOL, and the compiler could figure out what you wanted to do. And the COBOL compilers I've used, which were the one on Stratus computers, which I use at QVC, and GNU COBOL, have a switch to say whether you should use formatted COBOL, like the strictly formatted, the old-fashioned format, or free format. Which everyone can do that. And you would think that, how hard could it be to reformat it from one style to the other? But if you remember, we're thinking today where we have Perl, right? And we have systems to do that. If you don't have a language at your disposal that's really good at parsing text, and also your billing system for your company is running on this, and you don't want to screw anything up, and it's just easier to leave the code the way it is for the most part. I wonder how much code. I bet a lot of COBOL code in the wild still uses the old format. So what are our lessons from this? What? So I think the lesson is that decisions that they made at the time, which were perfectly reasonable decisions, can kind of come back and bite you. And vice versa, that you can take advantage of things at the time. So for instance, like Perl, what can you tell us about Perl? If you're a Perl developer in 2018, so Perl's a scripting language, and even the idea of a scripting language in 1959 would be kind of crazy. What do you mean you want to write a language? You're automatically 10 times slower than a compiled language. But it doesn't matter, right? Because it's still fast enough. It's kind of a crazy thing, right? Larry also designed it at a time where you could have hashes and dynamically allocated arrays, and memory was cheap enough that you could do that, and it didn't really matter that much. On the other hand, multi-CPU systems were probably not anything that you probably didn't realize in the mid-'80s that they would be so common. That Perl and Python both have issues that trying to take advantage of multiple CPUs is a really difficult problem. Python has that global lock that they still can't get rid of. Larry had to write an entirely different language to have threading, right?
I had to put off the whole multi-processing thing anyway, so somebody came along who was actually smart enough to design that part.
But it works great now, and it's.
Yeah, but I had nothing to do with the React and all those good things. That's Jonathan Worthington.
Think of with Steven with trying to add kind of first-class objects into the core of Perl has been also a difficult problem. That's because it wasn't anything that wasn't designed in from the start is often really difficult to add in. GPUs are another example. Anyone that's designed a computer system before the days of cloud computing and microservices, we're struggling this at my job that we have a big monolithic system that we're trying to break apart into services so we can scale things better. It's really difficult to do that if you haven't thought about scaling up front. Accessibility and Unicode, look at how much trouble still people have of dealing with Unicode in languages. I mean, C doesn't handle it very well. It's like null terminated strings in C that they can't get rid of. Probably we're all designing systems today that we're going to regret decisions we made today 5 or 10 years ago because we just never even considered that these things would be an issue. Just like having this design of the way punch cards worked was so firmly, deeply embedded in how COBOL worked that they couldn't get rid of it even today. Well, if you want to screw around with COBOL, there's an open source version of it. It began as Open COBOL in 2002. It's a part of the GNU family of packages as of 5 years ago. It's got a C API. I think people had asked me when I gave this talk before, what would you ever use this for? The two things I could think of off the top of my head were, one, if you had some code on a mainframe that you wanted to port to a Linux system, if you wanted to, I don't know, put something out on RabbitMQ or something like that, then maybe you could take up some of the code you had and do that. Also, if you had, the other thing would be if you had data that had been generated on a mainframe, in particular fixed format records with no delimiters, which still, there's still government reports, US government reports that look like that are challenging to parse in. You can kind of do them in Perl with pack and unpack, but it's unpleasant, and it's pretty straightforward to do it in COBOL. Otherwise, probably not, unless you just wanted to screw around with it and see how it works. So that's it. So thank you very much, and I think we still have some time. So thanks.